Hello students, today we are going to discuss very important chapter of abstract algebra. In group theory, we have a very important point, the center of groups. Before defining the center of a group, we want to discuss two terms first. First term, conjugate elements. If A and B be two elements of a group, then B is said to be conjugate to A if there exists an element X in G such that B equal to X inverse AX. If B equal to X inverse AX, then B is also called the transform of A by X. Thus, next, we define self-conjugate element. An element A of a group G is said to be self-conjugate if A is the only member of the conjugate class Ca of A. That is, an element A of a group G is said to be self-conjugate if Ca equal to singleton set of A. Thus, the element A of G is self-conjugate if and only if A equal to X inverse AX for all X belonging to G, or AX equal to XA for all X belonging to G. The center of a group. Now we define the center of a group. The set of all self-conjugate elements of a group G is called the center of G and is denoted by Z or ZG. Thus, the center Z of a group G is Z equal to set of Z belonging to G such that Zx equal to Xz for all X belonging to G. Example. Let G be the group of all 2 by 2 non-singular matrices over the reals. Then we have to find center of G. Let G be the group of all 2 by 2 non-singular matrices, the binary operation being the product multiplication of matrices, and let ZG be the center of G. A non-singular 2 by 2 matrix A, B, C, D will be an element of ZG if it will commute with every element of G. For example, matrix of A, B, C, D into matrix of 0, 1, 1, 0 equal to matrix of 0, 1, 1, 0 into matrix of A, B, C, D. If we multiply the matrices of left hand side, this becomes matrix of A plus B, A plus 0, 0 plus D, C plus 0 equal to 0 plus C, 0 plus D, A plus D, 0, B plus 0. That is matrix of B, A, D, C equal to matrix of C, D, A, B, which implies B equal to C and A equal to D. This is equation number 1. Again, matrix of A, B, C, D into matrix 1, 0, 1, 1 equal to matrix of 1, 0, 1, 1 into matrix of A, B, C, D implies matrix of A plus B, 0 plus B, C plus D, 0 plus D equal to matrix of A plus 0, B plus 0, A plus C, B plus D. By the equality of matrices, these imply A plus B equal to A and C plus D equal to A plus C and D equal to B plus D. Now solving 1 and 2, we find B equal to C equal to 0 and A equal to D. Hence, any element of matrix A, B, C, D of the center ZG becomes of the form matrix of A, 0, 0, A. Hence, members of ZG are 2 by 2 scalar matrices of G. Now, we discuss an important theorem of the center of Z. Theorem is the center Z of a group is normal subgroup of G. Proof. Let Z a small z, or we write for element of the group and capital Z for the center of the group G. Let Z be the center of a group. We have Z equal to set of Z belonging to G such that Zx equal to xz for all x belonging to G by the definition of center of the group. Here we have taken capital Z for the center of group and a small z for the element of the group G. First we prove that Z is a subgroup of G. For this, let Z1, Z2 belong to Z. That is, Z1 and Z2 are two elements of the center Z. Then, by the definition of center of group, Z1x equal to xz1 and Z2x equal to xz2. Again we have Z2x equal to xz2 implies Z2 inverse Z2x equal to Z2 inverse into Z1, Z2 inverse into Z2x into Z2 inverse equal to Z2 inverse into xz2 into Z2 inverse. By associativity, this implies Z2 inverse Z2 into x Z2 inverse equal to Z2 inverse x into Z2 inverse. Z2 inverse Z2 is identity element. So, this implies x Z2 inverse equal to Z2 inverse x, which implies Z2 inverse belongs to Z as Z2 inverse commute with element x of G. Now, Z1 Z2 inverse x equal to Z1 Z2 inverse x by associativity. This may be written as Z1 x Z2 inverse as x commute with Z2 inverse. This is equal to Z1 x Z2 inverse, which may be written as x into Z1 Z2 inverse. This means Z1 Z2 inverse commute with the element x of G, and therefore Z1 Z2 inverse belongs to Z. Thus, Z1 Z2 belonging to Z implies Z1 Z2 inverse belongs to Z, and therefore Z is a subgroup of G. Since we know that the necessary and sufficient condition for a non-empty subset H of a group G to be subgroup of G is A B belonging to H implies AB inverse belongs to H. By this theorem, Z is a subgroup of G. Again, let X belongs to G and Z belongs to Z, then XZ X inverse equal to XZ X inverse by associativity. We can write ZX for XZ. So this will be equal ZX X inverse, that is equal to ZX X inverse. Again, X inverse is an identity element. So this is equal to Z, which belongs to Z. Thus, X belonging to G and Z belonging to Z implies XZ X inverse belongs to Z, and therefore Z is normal subgroup of G. This is the very important theorem. Now we discuss another theorem. A statement is let Z be the center of a group G, then A belongs to Z if and only if Na, that is normalizer of A, equal to G. Further, if G is finite, then A belongs to Z if and only if order of Na equal to order of G. For proof, let Z be the center of a group G. Let A belongs to Z, then by definition Ax equal to Xa for all X belonging to G. Also, the normalizer Na of the element A belonging to G is Na equal to set of X, X belonging to G, and Ax equal to Xa. Now, A belongs to Z if and only if Ax equal to Xa for all X belonging to G, if and only if X belongs to normalizer of Na for all X belonging to G, which implies and implied by Na equal to G, since Na is subset of G. If the group is finite, then Na equal to G implies order of Na equal to order of G. Therefore, if the group is finite, then A belongs to Z, where Z is center of G, if and only if order of normalizer of A equal to order of G. Thus, we have discussed about the definition of center of Z and related two theorems very important in this chapter, the center of groups. In the next video, we shall discuss some more theorems of degree level. Especially this time we are discussing theorems of degree part third standard. For getting such theorems, videos of such theorems, please subscribe the channel. Thank you. Hello students, we shall discuss more topics and important topics, important theorems and problems of degree part third and other courses. So please subscribe my channel. Thank you.